Hello everyone, my name is Tiong-Sik. I'm from Yonsei University, and today I'll present my work, which is Fuzzy MP, a fuzzy digital signature scheme with biometrics. This is the outline of what I'll be presenting today. The overview. We begin off with an introduction, where we first describe some background of fuzzy cryptography, and also after that we'll proceed with the contributions of our work. In the preliminary section, we then proceed with some simple definitions and also some tools that are used to realize our scheme. In the next section, which is section 3, we then describe the fuzzy MP scheme, which is our work, in detail. Next, we then proceed to discuss the experiments and the analysis that are conducted on our scheme so far. Lastly, we then conclude our presentation in section 5. To begin with the introduction, so the usage of biometrics for cryptography is not new and can be dated back up till 1998. After that, in 2001, a biometric-based digital signature scheme was proposed, and it is based on the RSA and DSA algorithms. This signature scheme was rather inefficient due to the large primes involved in the RSA and the DSA. After that, in 2005, Sahai and Waters introduced the notion of fuzzy IBE. Due to that, many fuzzy crypto systems have emerged, and the fuzzy IPS proposed by Yang et al. In 2008 is one of it. The signature of the fuzzy IPS is generated where the private key is extracted from a biometric template. This is also known as the fuzzy extractor method. In 2015, Takahashi et al. Then proposed the fuzzy signature scheme. It adopts the generation of a fuzzy signing key, and it also uses the method of fuzzy extractor. The fuzzy signature scheme that was proposed requires the usage of a form of error correcting code, the ECC, which was also included in their work. In our work, we propose the fuzzy MP scheme, where we will make use of face biometric as a proof of concept for our fuzzy digital signature scheme. MP means monopoly, which is a short form of the monopoly commitment scheme, which is based on the monic polynomial. In our work, we utilize a combination of deep learning, biometric template protection, and also cryptography to realize our scheme. Different from previous works, we use biometric template protection to protect the raw biometric inputs, which was not considered previously from the previous works as mentioned. Also, we generate the secret key independently from the biometric template. This means that we do not rely on the usage of fuzzy extractor, and we also are able to reduce the risk of false accepts. At the same time, we also avoid the usage of ECC as well. As mentioned just now, we use the LFW face dataset for the experiments as a proof of concept. To begin with the preliminaries, we will start with the definition of a digital signature. A digital signature scheme has 3 algorithms: keygen, sign, and verify. During the keygen, a pair of public and secret keys are generated. Then, during the signing, given an input, the secret key and a message, a signature, which we denote as sigma, is generated. And lastly, during the verification, a verifier ensures the authenticity of the signature, which is sigma, with the help of the public key. So, if sigma is authentic, the verifier will return a 1 to accept the signature or 0 to reject it. This is the definition of the ArcFace model. So since we are using the LFW face dataset, we make use of the ArcFace model as one of our networks to extract the face features. The ArcFace model is a face feature extractor based on the ResNet CNN. And this is the loss function of the upface model. Then we proceed with the DRE. The DRE is our first form of template protection. And the DRE is able to preserve the distance between two encrypted vectors. So given a user secret key, which is USK, the encryption is performed with the help of a pseudo-random orthogonal matrix, M, pseudo-random vector, and with the help of pseudo-random permutation, we finally define the encryption of the vector as vector C with the help of the vectors and the permutation as follows. Next, after our encryption, we proceed with the IOM hashing. The IOM hashing was proposed for the purpose of cancelable biometrics. Particularly, we'll be looking into the GRP IOM hashing, which is the Gaussian random projection. For a feature vector X and a user secret key, first, we generate a random Gaussian matrix W such that W has this dimension. Then we perform random projection via dot product of the matrices to obtain the value Z. For each value Z, such as the row, we record the maximum index in the Q-axis to obtain the hash codes. Since the maximum index is in integer form, the hash codes written are also in integer form as well. Next, we proceed with the monopoly commitment scheme, which was proposed by Tan and Gross. The monopoly commitment is the essence of our scheme, and it is proposed for the privacy of multiple attributes. The monopoly commitment scheme is described as follows. We begin with the setup by generating the groups and also a random integer. Then we calculate the public keys A and X and return them as follows. The public key also includes the groups G1, G2, GT, and also the bilinear pairing E. Then we return the secret key as X, which was generated earlier. During the commit stage, given a set of attributes A or also a message, we then generate a random opening value O. This A is as the set of attributes. We will be using the biometric template as the attribute in our scheme. With that, we generate the value of MJ via MP encode. Then, we produce the commitment value C. This is during the opening if the values of A and also O and C are exact. However, since biometric values are not same, given a threshold, which we will set as L, we perform WJ via MP encode of the intersection between A and I. This threshold is the one that determines whether the query and the enroll biometric templates are able to meet the certain threshold or not. If it is able to meet, return the intersection set, which is the intersection of the query and the enroll template, and also the witness W. And then this is the check equation to verify that the intersections are correct. We first compute IJ, M1J, and also M2J. Then we perform the verification by using the bilinear pairing. Based on the modules described earlier, this is the overview of how our scheme works. As mentioned, first we extract the biometric template using upface with a dimension of 512. After that, we then encrypt the extracted features using DRE with the help of a user secret key. Then, we perform the hashing using IOM hashing. And then, we are able to get the value of 5x. This 5x is the attributes set in the signature, and with the help of PK, SK, and the message, we pass it into the fuzzy MP and we are able to generate the signature sigma. Similarly, during the verification process, for a query template X prime, we generate using argface, DRE, and then with IOM, we get phi X prime. With the threshold and also the signature, we then pass it inside into the verification scheme, and the verifier will decide if this hash code is able to be authenticated similarly with the value of sigma. As mentioned earlier, this is the algorithm of the fuzzy MP signature. So this is already described earlier, and this is the fuzzy MP signature part. So we first generate the secret key and the public keys where they are actually selected independently from the biometric features since they are not involved. And then during the signature, we pass the biometric template, the hash codes, as well as a public and secret key to generate the signature, which is T, S, and V. For the verification, which is similar to the signing as well, we first extract phi X prime, and then with the threshold, we compute the witness prime, and we check whether this phi X prime is able to beat the threshold, and we verify the intersection between the signature and the hash code, biometric hash codes. Moving on to the next section, which is the performance measurement. This is the performance of the feature vectors, which is before the fuzzy MP signing. So this is the ROC curve for argface, DRE, and IOM. As you can see, the argface and DRE has rather similar EER, and there is very slight loss of performance during the IOM. However, this EER is still considered quite low, as you can see based on the curve. Moving on to the performance of the fuzzy MP signature. So with corresponding values to the Q in IOM, these are the ER for the fuzzy MP. These ER values are generated in terms of Hamming distance. In comparison with this, the argface, DRE, and IOM feature vectors, they are using the cosine distance. This is the simulation and complexity which is needed to run the fuzzy MP signature algorithms, and it can be noted that the timing is still quite large. The reason is due to that we are using Python to run the experiments, and perhaps if we could apply some parallelization or use some GPU to run the algorithms, it will definitely take a much shorter time to execute these algorithms. This is the unlinkability analysis based on the protocol by Gomez-Barrero et al. In 2018. It is noted that if the unlinkability analysis, the global D score is 1, it is shown that the feature vectors are very linkable, and if the value is 0, the features are not unlinkable at all. It is shown that for both DRE and IOM, the global unlinkability D is 0.1, which is still quite a satisfactory value. To conclude the presentation, we have presented a fuzzy digital signature scheme, which is the fuzzy MP. The fuzzy MP utilizes the biometric templates to generate its signature as well as its verification. So, using the LFW face dataset as a proof of concept, the fuzzy MP is overall able to achieve a satisfactory EER in terms of verification performance and also able to achieve good unlinkability. However, as mentioned earlier, the fuzzy MP performance can still be improved in terms of the simulation timing by parallelizing and using a GPU to run the simulation. These are the references that I have used for this presentation and also for the work. Thank you for your time and thank you for listening.